in this segment, we're going to take a look at 3 different hypothesis tests. One of them is going to use the z-stats, one of them is going to use the t-stats, one of them is going to use proportion. We'll also have a mixture of whether we're working with raw data or just with a summary of that data as well, so we can see how those different options work. The first situation that I want to refer to is actually taken from page 376 and 377 in your book. It's problem 7.33. And essentially the idea here is that they're trying to find out if by using cartoon and kid-friendly packaging on healthy foods, it can actually make the kids more receptive to eating those foods. They've done a preliminary study. They've found out that the average willingness to eat sliced apples for kids is a level of 3 out of a scale from 1 to 5. And now then what they've done is they have done a different packaging on these sliced apples, put a cartoon apple that's smiling at the kids, and they show them that packaging and then ask them about their willingness to eat those apples. And they want to see if that actually improves the children's willingness to eat. They conducted this study. They actually showed this packaging to 408 school children. And the average willingness to eat score was 3.69 with a standard deviation of 2.44. Well, that's taken from that problem, 7.33. And our hypothesis is that the mean with this kid-friendly packaging, that our population mean actually will be greater than 3. That the packaging has actually improved the children's willingness to eat. That's what we believe. That's what we think we're going to be able to show. The opposite then, our null hypothesis, will be that the mean is equal to 3. Again, generally we would say less than or equal to, but for the StatCrunch software they just use equal to there. Either way, it's the opposite. It's our nullification of what we really believe. And so this is quantitative data. We have a mean, we have a standard deviation, so we have to decide, are we going to use z-stats or t-stats? We have 408 observations here. 408 kids participated in this survey, so that's going to be z-stats. Let's see how that works in the software. We'll go to the stat button, go down to z-stats. It's a one-sample test, because we just have one group of kids. We don't have 2 different groups. We'll get into that in another couple of weeks here. But one sample, and we just have summary information. We don't have the scores for each of those 408 children. We put in our information from the sample. Our sample mean from the problem was 3.69. Our standard deviation was 2.44. Our sample size was 408 children. We wanted to perform a hypothesis test for the population mean. Our null hypothesis is that the mean is equal to 3. Our alternative hypothesis is that the mean is greater than 3. So we put that in and we hit compute. We can see that the sample mean was in fact 3.69 as the problem had told us, and our p-value here is less than 0.0001. There is less than a 1 in 10,000 chance that we would be making a mistake, that we would be wrong in concluding that the population mean is truly greater than 3. Keep in mind, we're making this inference about the entire population of elementary school age children in the U.S. We're talking about millions of children. We have used 408 of them in our study. So a very tiny fraction of the total children in the population, and yet we're able to say with virtual certainty here that this packaging does in fact make children more likely to eat the apples. All right, let's look at a different problem. This one is taken from page 384, problem 7.52. And we're actually going to use a data file for this one. It's in our Chapter 7 data, and it is called traps. This data has several different things in there, but the left-hand column called trap spacing deals with how much space there is between lobster traps. There's a regulation in Baja California, where this data was taken from, that the lobster traps have to be placed an average of 95 meters away from each other. And so this governmental agency has come in and they have measured the distance between traps of this particular company, and they're trying to find out if this company is violating the policy or not. They have to be 95 meters away. They can't be significantly less than 95. They can't be significantly more than 95. We have our data here, and we also have only 15 observations. So this is going to have to be a t-stat. We'll go to stat, t-stats, one sample with data now. The column that we're interested in is trap spacing. And for our hypotheses, our hypothesized value is 95, because it's 95 meters that we're testing against. And now in our alternative hypothesis, the sign that we need to have there is the default here of less than or equal to. According to the regulation, it can't be much less than 95 or greater than 95. It's supposed to be right at an average of 95 meters between the traps. We'll click compute. We get a p-value for this one of 0.99. 99%. Our sample mean was barely over 95, 95.06. Now technically, that sample mean is different than 95. It's not equal to 95. It's slightly off. But we've just taken a small sample, and if we were to conclude that it's anything other than 95 meters based on this sample, there would be a 99% chance that we would be wrong in that conclusion. So here, with that p-value being greater than 0.05, we would not reject the null, or fail to reject the null. We definitely haven't proven that for this company they do have exactly 95 meters on average between all of their traps, but we definitely have failed to prove that it's not 95. The last example that I want to take a look at is taken from problem 7.72 at the bottom of page 392. And in this particular study, they were trying to figure out if gummy bears of different colors actually produce different taste sensations. So what they did is they took a group of students. There were 121 students that participated in this survey. These 121 students were blindfolded, and they were given either a red gummy bear or a yellow gummy bear. Now, if taste was not a factor, then we would expect, and they were blindfolded, they were given the gummy bears, and they were supposed to identify or guess which color they were tasting. if taste was not a factor, we would expect that half of them would guess red, half of them would guess yellow, because there really would be nothing to differentiate their guess on. This is a proportion test. So our alternative hypothesis is going to be that our proportion is different from 0.50. If taste makes a difference, then we won't end up with a 50-50 split. And the null hypothesis, if taste doesn't make a difference, we would end up with a 50-50 split. Out of these 121 students who were given a red or a yellow gummy bear while they were blindfolded and asked to identify it, 97 of them actually correctly identified the right color while they were blindfolded. So let's see if that proves that taste does make a difference. We'll go to stat. This is a categorical or qualitative variable, so we go down to proportion stats. One sample with summary on this one. We had 97 successes. Remember that a success here simply means we found what we were looking for. We're looking for people who correctly identified the color. 97 successes out of 121 observations. Our hypothesis test is actually correct by default. We're looking to see if the proportion is different than 0.5 or 50%, and the null hypothesis is that it is equal to 0.5. We click compute. We see that our sample proportion actually showed that 80% of those students correctly identified the color, and if there was no difference in taste, that's going to be highly unlikely that 80% of them are just going to guess right. So our p-value here ends up being less than 0.0001 again. There's less than a 1 in 10,000 chance that that happened by chance, and so we can reject the null.